If you like this video, make sure to visit our Vimeo page and follow us to get the latest update.
Hi, Austin. Good evening.
Yeah, hi, Shasha. Have you gone through that logistic regression session?
I'm sorry.
Logistic regression session. I think you're not there in the last
Last
class.
Sunday you have covered logistic regression. No, I didn't go, but I understand the logistic regression, so it's fine.
Okay. So in that case, I think Senta was there on that session. Okay.
So just a quick one. Whatever the source code file, have you uploaded in the portal?
No. We are covering the code part today. We had just covered the theoretical aspects of it on that day.
Oh, okay.
So we are covering and we'll start with a very simple exercise like that we did in linear regression, that SAT, that kind of thing. So I'll try to speaking less today, and I'll just take you through the code. A lot of it you'll be anyway understanding, and wherever it's necessary I'll speak, because I just don't want to strain my throat too much.
Yeah. No problem. Take care.
Okay.
And about the linear regression source code, is that source code available in the portal?
Yeah, that is uploaded.
Okay, perfect. Thank you.
So we'll start with this first. So I'll start to write the code. It will be quite similar to what we had done in the linear regression. I'll start with the data. So you just let me know if you feel any confusion. A lot of it is going to be similar because we have covered linear regression quite quickly. So. Sure. So this is the data frame in which it is very simple the way we started off in the linear regression part also. It has two records. essentially. One is simple SAT score and whether the person got admission into a college or not based on that SAT score or based on that SAT score. So we have some data points here. About 167 or 168 data points are there in this. So we are just going to we'll give it with one one variable right now just for the understanding sake, and then later on we'll do some example with multiple variables. So so the question part is clear, right? That we are going to see that whether the person got admitted. We're going to basically predict whether the person got admitted based on the SAT score. So is that clear, Sinta? Like we're theoretically trying to understand it in the last session.
Yeah.
Okay, so we'll do it now in this part. So simple, the same things mostly we'll do. No ideas this one. So over here we are just making that yes, no as 1 and 0. Now this has become all 1 and 0. So now on the similar patterns, we'll create this dependent variable. So, data admitted is my dependent variable, and x is, so we have only one variable, so that's one data, and we're calling this as SAT score, right? So SAT. So that's it. So these two are my independent and dependent variables. So we can just see, I mean, like we can do some basic, x, y. So just wait, I will plot this. It is not going to be, you know. So if you look at it, it's a very, because the values are either 0 or 1. So admitted is either 0 or 1. And with the SAT scores, whatever, uh, it is kind of, only 2 points. And it's not scattered as in,
Sir,
yeah.
last class we also discussed in this S curve in the case of logistic regression.
Yes. So we'll come to that part as well. So
Yeah.
it's just that I mean, like, because the value can either be 0 or 1, so that is what it is showing. So
Okay.
if you remember from the linear regression, because linear regression, and we were discussing it quite detailed in the last session, that this one line cannot fit here, right? If you put some line here, it does not make any sense, because then it will mean that if the SAT score is 1700, then admitted score is 0.4. So that doesn't make any of a sense. Like in the way we basically understand linear regression. So in that scenario, it will kind of curve in. So we'll see. Like, if let's say that if we're trying to understand it with linear regression, so we'll start with that only. So what I'll do is I'll import the stat model also. Import stat models. Stat model. Okay, so what we'll do is,
Stat models.api as SM.
okay.
Yeah.
So what we'll do is we'll just try to plot that, see that linear regression which we have seen, that whether linear regression will suit this data, and we know, like, we know by understanding now that linear regression will certainly not suit this data. So just put the way we do it in SM. But we'll add the constant of ones. So I'm just fitting in this linear regression. And we'll fit this. So it's just the linear regression that we're trying to fit. Okay. So you know now that we can actually do the prediction part of it by just multiplying it by the coefficients, right? So coefficient is we can see results dot lin. This is summary. So you will see this, right? The coefficient now is this minus 3.259. So if you want to get this, predictive equation, we can simply use this multiplication and get that predictive equation. So what we will do is, so this y predict can be defined as um, x1 cross uh, minus 3.2, right, plus this. Sorry, this is the number. So this is actually, this is a constant part of it, and then plus multiplied by x1. X1 is actually the status code 0.00. So right, this gives me the predictive equation in a way for this linear regression. If we try to fit this data, because we know this will not fit with the linear regression, but we still try to see what actually happens out of it. So and then we can sort of plot this. So we can, it's not a scatter plot, it will basically a bit line plot. So we'll just put PLT plot x1 y thread PLT plot. Okay, and then we'll just put these two things. So we can directly copy it from here. Okay. And what we want is we can also keep these two lines, the scatter plot also. So this is a line, but then we can add this scatter plot also, so that everything will come in one picture itself. Okay. So now Then x1 and squared we are predicting. Okay. Okay, so okay, one second. There's some problem here. Results link dot summary. So this is fine. This is actually 0.002. Okay. Yeah, because that was looking quite weird by just by look. Okay. So now if you look at it, this is how, if we go by the linear regression, this is something that we'll get. Now, there are some problems with this line, if you look at it. The problem is, one thing is, because now let's say that if you're saying that 1700, so it does not mean anything like 0.04, so you cannot say what is happening here. Right? The bigger problem is, we know by now from the last class that these can be thought to be as probabilities. If you think of it 0.02, 0.01, 1.0, so they can be probabilities. So we can say that, okay, 1700, then the probability will be point something around 0.04 or something. But the problem is, this is not the issue over here. The thing is, even, if your SAT score is low, then it is like, negative. You're getting my point. So this curve, I mean, it cannot go above 1, it cannot go below 0. That is definitely not a possibility. We can, transform the data into logarithmic case as we are doing in this logistic regression. So the number still will be, I mean, if we are calculating the probability of odds of success, then that number will still be in the range of 0 to 1. It can definitely not go, less than 0 or more than 1, right? But then if we go with the linear regression concept, then it is showing that if if the score is something around 1350 or something, in this range, lower scores, it means it will have negative probability. So it does not make any sense. If it is very high, more than 22, 2200, then it is showing around 1.3 as a probability. So that also does not make any of the sense, right? So in this case, the linear regression is definitely not is not something we can go ahead with. So that is what you are asking, Sinta, that this curve cannot be straight. Somewhere down the line, this curve should kind of shift, right? So this should, if the scores are low, it should be like somewhere very close to 0. If as the score goes high, it will go very close to 1. This is what you are asking, right? The S curve, Sinta. Hello?
Yeah.
This is what your question is, right? You said that,
Yeah.
so basically, obviously, this cannot go, above 1, and this cannot go below 0. So this curve should somewhere tend like this. This is how it should become, that when the scores is going higher, then it will be close to 1 or like 80%, 70%. So as the score goes higher, this is how the trend should look like. But definitely, these two parts should not come in. So this means that obviously linear regression is not a solution for this. We are just trying to, because you asked the question, so we're just trying to see whether if linear regression can work around. So what we'll do is, we have another thing, logistic regression. We have seen this, and we have seen it quite detailed. Some part of it we'll still see, but then that sorry, that how basically the curve will shift. We'll try to come to, so there is logistic regression. The way we have, this linear regression, we have also logistic regression. So let's say we are trying to play this logistic regression model now and see how this curve will shift. Okay, before going to logistic regression, okay, we'll do one thing quickly. I think on that notes. Okay. So last class, what we were discussing is, you know, that the way right now we have done it like y equal to a0 plus a1 x1 plus a2 x2 plus like this. Right now we have one variable sat. Sorry, one variable x1 is sat here. So on the similar way, what we had come up to is this logistic regression takes something like this. A form it takes is something like this. Log of p by 1 minus p is equal to a0 plus a1 x1 plus a2 x2 and so on and so forth, right? So now we can very easily, so this is just a mathematical equation here, right? There is nothing big about it. So like let's say that I'm just calling this part as m or something. Okay, m I am just calling this particular part. Okay, so then it becomes like if you remember from your logarithmic and exponential class, if you remember, which you might have learned during your school days or in college somewhere, that this is basically natural logarithm. So if we take this equation, we'll make it like log of p by 1 minus p is equal to 1, and so this takes something like log of p by 1 minus p is equal to m, where m is just the the right hand side of the equation. So this also becomes p by 1 minus p is equal to e to the power m, or you can calculate p from it very easily, right? So it's nothing but p equal to em, and so basically this is something like 1 plus em, or where m we know that this is a number a0 plus a1 x1 plus a2 x2, right? So this is how the equation will become. Clear? There's no doubt about it. Simple. Just we have changed this logarithmic to the exponential equation. Am I clear with this? Sintra and Sisir?
E raised to m.
No. So you remember the question? The equation that we had is like log of p by 1 minus p.
I got it.
Equal
Is
to
equal to a0 plus
right?
a1 s1.
So this is nothing. So this is the thing. Now if you take, so this is the natural logarithm. You remember this is natural log. So if you want to convert it to like p by 1 minus p, then it is basically e to the power m. If you remember, so this is just a simple mathematical formula, like ln of x is equal to something b, then x equal to e to the power b. This is how it becomes.
Okay.
Okay, so this is just a mathematical form of it. So this is what we are doing the conversion. So basically p by 1 minus p is e to the power a0 plus a1 x1, right? I'm just calling this as m for now, just for writing. Okay, so e to the power m, and then so basically the p becomes e to the power. So basically this is nothing but p is equal to, this is another way of writing it, a0 plus a1 x1 plus a2 x2, and like that, by 1 plus the same number. Okay, this is how we can get the probability, because otherwise the equation that we'll get will be for this, right? Log of this number. This equation we'll get, but now we want the probability, because probability is what is going to lie in the range of this number, right? Am I clear now?
Yeah.
So we are just trying to get the probability from log of p by 1 minus p. We are trying to get this probability number. So we'll use this equation, the same logistic regression we'll use, and we'll try to figure out this number, right? This is what we want to figure out. So we can do it very easily mathematically. We'll come to that. Okay. So what we'll do is, the way we have done the linear regression, so we can do it for logistic regression also. Like, let's say that regression logistic is nothing but a very simple formula, sm dot losit we call it. Okay. Sm dot losit, and the same y and x can hold here, because you have given this. Yeah, y is this, and x also we have added the constant, so not a problem. So same y and x we can pass, because we are doing the same thing now with the logistic regression. And then the same way you can basically fit the model. So results of logarithmic, it is okay. Now you can just store this using the fit results of logic as res log dot fit. So it's just the same thing, absolutely the same thing. Is log dot fit. So we are basically fitting using the same data points. Now, so this is okay, and so this basically uses at the background the machine learning, wherein it iterates for various systems. So this is what it is showing here. We can look at the summary also. So results log results. So it will also have the similar kind of summary, right? The way we have for linear regression. So parameters will obviously be different. But then one important parameter like p-value, remember, so it's the same here. If it is like less than 0.05, then that becomes very significant. And we'll understand some other parts of it also, that what is important, what is not important, and what these variables basically mean. So before that, what we'll do is, before understanding the summary statistics of it, what we can do is we can actually understand the curve. We can understand the curve by the curve, that whether how the curve is basically looking. So what we'll do is we'll plot the curve, and we'll later come to the summary part. And we also know that this coefficient is required, like the way we have used this for linear regression to plot the coefficient, plot the line here. We'll use this coefficient to plot the line. Okay. So what we'll do is, so for plotting it, if you before that we need to actually define. We can either do exponential. So basically, we'll have to write this exponential equation that we are, seeing here. So we can write this equation, let's say by f, and rather than this, we can do one thing. And p.exp and b0 is nothing but this number. Okay. So we're just getting the probabilities, nothing but actually the probability number we're trying to figure out, which is basically e to the power, b naught plus b1 x1. So if we are getting the constants, okay, plus 0.0420, okay, 0.0420 into x1. All right. We'll sort this number also later on, but for now, just keep it like this and divided by e to the power b naught plus b1 x1 divided by 1 plus this same number. One plus the same. So this is actually the probabilities, okay? So you remember the probability function that we were just saying, which is basically e to the power. We have just seen that. So we have just converted it to this number. Let's see if there is no error, it will run. And one thing more we can do is we can actually sort this number by either serial numbers or we'll sort this number so that basically it will increase or decrease in the same order. Okay. All right, so this looks fine. So let's have a look at the probability numbers. Okay, so this is all less than 0. So obviously it's fine. Okay. So what we have done is we have now calculated the probability for each of the SAT scores. Based on each of the SAT scores, we have calculated the probability value. Any doubt here? What we have done is just the same equation that I have put in, which we have just seen on the whiteboard. Right, this equation actually.
So where will you get this data in 69.912 and 0.0420?
So okay, I'll tell you. This is the equation that we have just seen, right? The probability value is exponential
Yeah.
of A0 x1. This is what we have done. And
Yeah.
I'll show you where we are getting this data. That is why we're looking at the summary part of it, right?
Okay.
So in the summary, if you look at it, this is a summary that we have just seen, right? NP log summary. In that summary, we are getting this coefficient -69,
Okay.
right? B0, and the way we have in the linear regression. B0, this is the
Okay.
B0, and this is the B1. Okay.
Okay.
From here, we are getting this number. Now it is clear?
Yeah. Yeah. Okay. Okay.
Okay. So we have defined the probability, and also what we'll do is we have just sorted it also in one order, and we'll sort X also. X is nothing but that X1 number, so that it will be easy for us to plot. So we'll say X sort or something is equal to NP dot sort. So these things are part of NumPy functions. So NP dot array action. Okay, so we have sorted these two things. Now it will be easier for us to plot these. So now if you plot this probability, so this probability will always be between 0 and 1. So basically this line will kind of curve now. And it will tell us that at what value of x1, which is basically the sort, the SAT score, what is the probability of selection. Okay, so we'll quickly plot this curve. Okay, x1 and y. X1 is the data that we have, and okay. Now, is this the same thing for x level, y level? So there's nothing here to change. It's basically we'll just put these two things as labeling of points, and then what you do is we want this line actually to be fit in here, wherein basically by the probability we want, so I can call it probability sorted also because we have sorted it. So it's not a name, like it's just a name. So it's easy to read it. Now we can do PLT. So this will basically plot the line, this line, wherein we are giving these two things, X sort and the probability values. So X sort and the probability sort values, P sort, which will be basically on the y-axis, and X sort is x-axis. Okay. Now, so we can give it some color also if we want, like color, or otherwise we'll just be blue. Color equal to anything. We can put like C something or red. Okay. And then plot zone. So now we'll look at this. So can you see the difference?
Yeah.
Right. In this case, if you're doing linear regression, the
Linear
line will
regression
cross.
curves. And
It will cross, which is not good. This means this is fine.
it's curved.
And when now this curve has curved. So one very good thing that we are saying here is that when the SAT score kind of increases, right? As the SAT score is increasing, we are seeing that the probability is very high, like it's almost 90% and like that, right? It will never be 100%, it will never touch 100%, but it is very high, right? So that is how it should be. Like if the SAT score is low, it will be kind of towards 0. And as the SAT scores, like let's say that if someone has a SAT score of let's say 1700, so the probability is somewhere around 80%, right? So it makes sense also. The higher the SAT score, the probability of getting admission is higher. Is this clear now?
Austin, I have a question. P
Yeah.
sort, I understand that you sorted it, all the probabilities.
Yeah.
What is X sort? What exactly you done in X sort?
XOR is nothing but these numbers only. Like in the data, by default, X was randomly, like it could be any number, right? In this order. So we have just sorted it in the ascending order so that if we are plotting it, so it will be in the same order. You're getting my point? Otherwise, it will not be like, because we want to see it on the graph. So what will happen if you don't sort it? You can plot the graph, that's not a problem. But then if you have sorted it, then whatever is corresponding to 1300, that probability will come first. And whatever is like in that order, basically in the increasing order of the status code, the probabilities will be given. That is why we have sorted. Is this sorted? So now you see this difference, right? This line is linear, and this is very much a non-linear line. So logistic regression is a non-linear curve. It's not a linear curve. Okay, so it's a non-linear model. So if you see some situation wherein it's a justification of 0 and 1 kind of situation, and data is also in such a way that we're seeing it is highly similar to even the assumptions are highly similar to the linear regression. And if that happens, then you can go ahead with the logistic regression curve. So now this curve actually gives you that what is a probability. So these are all the probabilities. So you can write that this is not essentially admitted now. If you want, you can also call it like, probability. So this is actually the probability. We can change the Y level. So this is a probability. And based on the SAT scores, you can have the probability that what. Now, once you have come to this point, right? So I'll again go to the drawing board. I'll explain you one thing. So now what we see is we have a situation wherein so basically the probability starts from 0 and it is going to 1. Okay, and obviously like if the scores are low, then the probability is somehow lower, and then if it is increasing, then it's going like this, right? This is how it is, the curve is looking like. So one thing is, so, and based on every point you have some probability values based for all the SAT scores. Okay, these are SAT scores from whatever range, 200, 200, whatever. Okay, so this is how the SAT scores are, and based on that we have the probability like 0 0.2, 0 0.4, 0 0.6, 0 0.8, and so on and so forth. Okay, so one thing is, now how do we define? We know, see, the question we are trying to solve from the beginning is if the person will get the admission or not, right? So if the admission is possible or not, and we said that it will be a very kind of 1 and 0 question which we cannot like directly answer because there is no guarantee. So we have come to the point that okay, what is the probability of someone getting? So if there is a probability, like if someone has got a score of 1600, what is the probability that he will get the admission? So we will get the equation like this. Now from here, and like this for all the scores, now we can have like different scores, 1600, 1650, 1625, 1650, like that. We can have multiple scores, SAT scores. Similarly, we'll have the probability, like, or let's say somewhere around 1800, 2000. So obviously for this, based on the model, we'll see that this is like high probability. This could be like 0 0.9, 0.85, 0.7, like let's say, or if it is 1400, then it will be like 0.4. This could be like 0.5, 0.6, something, some probabilities values will be there. Now the thing is, still we have to come to, this is a probability, but we have to define that yes and no question is still not defined, right? That whether this guy will get the admission or not. So based on this probability, we can put some cutoff. Like let's say that you are putting a cutoff of 50%. That if the probability value is more than 50%, you may say that okay, these guys will get the admission. And if it is less than this, you say no, these guys will not get the admission. Or so this is a kind of thing that you have to kind of keep in trade-off. Like this is your call, that at what constraint criteria you want to give that flexibility, that whether this person will get whether you want to say that okay, this person will get the admission or not. Because for you the matter is this, though you have got the probability, but still if you have to say that out of now we have 1000, you have got a new 1000 students, right? based on the model, and we have their SAT scores. So based on the SAT scores, if we have put the criteria like probability is greater than 70%, then we may have like only 20% of the people who will fit into this criteria. So we can say that okay, based on more than 70% of the criteria, only 20% people will get the admission. So you have to come up with some number and you have to fix some threshold based on this. And that will be your call, that what threshold you want to be. Let's say for now we'll just keep like this. If it is the probability is more than 0.5, let's say that person will say will get the admission more than 50%, or it depends like what call you want to make, more than 70%, more than 80%. If the colleges are very good, right, then they may be having higher SAT scores as a threshold. So for them you may also have like more than 80. If the probability of getting this is 80%, then only the admissions will happen. Or it may also depend that if the seats are less, then also the probability value needs to be higher. So this call depends on the business context, based on the understanding and the number of seats available in the college. So this number can always vary, but this is how the concept will look like. So basically, if you have to define that how many people or who will get the admission, at what threshold you want to say that this person will get the admission and not get the admission, this will what it will define actually. Am I clear? Hello?
Yeah.
This
P
threshold.
value is greater than 0.05 or 0.5.
Yeah, 0.5. It's not 0.05. P value is greater than 0.5. So you can see that what cutoff you want to. Basically, it depends a lot on the business context we are handling. But logistic regression will throw out the probability values of the admission. So this is how it is. It will look like now. So let's say we'll for now keep the probability as greater than 0.5. That if the person is getting 0.5, then we'll say the admission will happen. Okay. So we'll come to some other parts of it. We'll first understand the summary statistics. We have seen some of them, that how this model basically looks like. So okay. So this graph now you understand is a S-curve. So let's understand this part a little bit more. The summary statistics. Okay. So few of it you are very familiar by now, right? That this thing, p-value. We remember it's the same concept as linear regression. If the p-value is less than 0.05 at the 95% confidence level, you'll keep those variables. And the same concept will apply. Right now we have only one variable here, SAT. But then if you have multiple variables also, right? If you have right now you have SAT score, maybe you have their previous academic results also, and many other factors, many other factors can play. So if you have those kind of results, you can add all of them, and you can either go, as we have done in that we have seen examples of forward selection and backward elimination. So you can go ahead and you can figure out that what equation will basically hold, and you will finally freeze the equation in the same fashion that we did in linear regression. So we are just using right now one example. Now, apart from it, you see a couple of things. Like the same way we have dependent variable which is admitted, model that we are using is model. Method is MLE. MLE we have discussed. It's a likelihood function. Basically, it's it's basically MLE basically tells you that it's maximum likelihood estimation. So it always based on the likelihood function, and that likelihood function estimates the likelihood of the model to describe the underlying relationship. Like we are talking about the similar thing in the linear regression also, that how much variability is basically being explained by the independent variables. In this case, we are trying to say that how much of a relationship is basically being established. So that is how the likelihood basically function. So bigger the likelihood function, the higher the probability that model is correct. So that is what it means. That if the likelihood function is more, then it means that the model is highly probable that it is correct. And this MLE method, what it does is, like we are using OLS method, ordinary least square method in that. This MLE method basically tries to maximize the likelihood function. So that is what the role of this MLE method is. So that's why, and we try to essentially use this because this is a probabilistic model wherein likelihood function works best. Now, so these are just whether it has converged or not. So it's converged is fine. Beyond that, what is more important? One more important parameter here is log likelihood, right? You see this log likelihood. This tells basically as we have seen. So this is also based on the likelihood function also. And the bigger this number. So right now this is negative, but then it's not necessary has to be negative. And if it is negative, and then so it means that if minus 21 comes by running different models, then that is better. So if the number is bigger, right? If the number is bigger, then that means your model is better functioning. This is, or you can say that this likelihood function is getting increased using the MLE method. So this is what it means. So so basically log likelihood will work in situation when you have different models. Like right now you have SAT score only, but if you have, like, let's say 10 variables or 20 variables, you are running the model continuously, and like the way we are trying to look at RS square in that, something like this we can basically look at here in likelihood. And then we have this pseudo R square. So pseudo R square is not exactly R square. It's just a kind of analogy of what we have learned in the linear regression. This also gives you similar kind of understanding that how much of it is being explained. So if the pseudo R square is, I mean, obviously, like if the R square is higher, it means the model has explained that much. It is basically carrying that much of explanation of the variation. And different models will have very different R squares. It's not necessary. It will have completely different R square. And this R square is also called McFadden R square. I mean, because it has been described with McFadden. And one thing about this R square is this will again be used when you are having the same data points. I mean, like same model. You're basically reiterating it and figuring out what is happening. This number, if it is in the range of it's not like it will continuously increase. So if it is in the range, like the general range would be something between 0.2 to 0.4. If it is in that range, this means that your model is quite good as far as pseudo R square is concerned. So they have calculated this statistically that range, but it is not a mandatory thing, because many a time, maybe because of the lack of data or lack of business understanding, we will never be able to arrive at those numbers. But usually it is in the usual context, if someone asks you what is a good R square range, pseudo R square range, then that range is like 0.2 to 0.5. So that is something you need to keep in mind. Okay. That range is like 0.2 to 0.4. May not be always practically possible, but that is the appreciable range for pseudo R square. Apart from this, we have two more parameters, LL null and LL, log likelihood null and log likelihood p-value. Okay. So this p-value again has a similar connotation from that f-stat connotation of linear regression. If you remember that if the p-value is less than 0.05, this means that this model is working fine. I mean, like the values that we have given to this model is essentially kind of adding to it, right? This basically is kind of giving it some explanatory power. How we are going to compare this is based on the LL null. So if the log likelihood that you're calculating, right? So this LL null is basically in the situation when all the values are 1. When all the values are 1, then this value will come out to be -115. So if this value is significantly less, like this log likelihood is significantly more than this number, as in this case we are saying minus 23 is quite more than this minus 115. So if this number is much more than this, then we can say that statistically this model is giving us some explanatory power using this particular variable. If we did not have this variable, then the explanatory power of the model will be less. So this is how it means. But what we can also see is, if you want, we can check this number, that if we just give 1 as a variable, right, rather than using SAT, we only use, let's say, an array of 1, only 1 as variable, then this log likelihood and this LL null will come out to be 115 exactly. So we can actually do this also. One second. What we could do is, so right now what we'll do is just simply we'll create with only 1. Okay, so let's say we are just right now we had sat score as X, so we'll just create 1, which is basically just add constant. Sum dot add constant. And then you can simply use these 2 things. Okay. So instead of using SAT as the variable, I'm only using 1 as the variable. Okay. So if I put this, so if you look at X, it has only 1. There's nothing else in this data set. This is just a variable of ones. Okay, so this is basically what we could do is, okay, otherwise there's another way of doing it is, we have data.info. Okay, so it has 168 rows, right? So what we'll do is we'll create a constant of only ones, 168 ones. Okay, so simple NP ones we can use. So let's say I'll just put const as np dot ones. This is a function simply which will create a 1, nothing here. Np dot ones, and how many we want? 168. So this will work. Yeah, now this is fine. And so if you look at this const, so it's just ones, right? It's just an array of 1. We'll use this to build the model. We are not using SAT score to build the model. we'll only use this to build a model. And what we'll do is, so let's say, and that's what we are basically trying to see, that that 115 number is actually coming or not. So you can say it as like something as null, because we are just trying to create this null situation. Null. And our independent variable in this case is const. Okay, it's not x, is const. So, okay, okay, okay. Sorry, this is null. Right? This is null. And this is. Yeah. So see, what we have done is we are running this logistic regression with only ones. So basically, like, we are just trying to find the probability based only on the ones. So if you see these both numbers, log likelihood and this log likelihood and LL null, both comes out to be the same. And then that this case the p-value will not be defined because it's not mean anything. So basically, we are not adding any value to it. It's very infinite. It's kind of infinite. So if this value is significantly reducing, if this log likelihood value is significantly reducing, then it means that the variable, the independent variable that we have added is adding to, adding to the information in the model and is basically creating the significance in the model. So that is why, that is what this essentially does. That if it is less, if you only add one, then this log likelihood will also become one. And if this value is significantly less, that significance will be defined by LL or p value. So if your p value is very less than 0.05, it means that your model is significant. So these are the important parameters that you need to basically look at when you are doing the logistic regression. And obviously you have to iterate it based on the p values. So if the sum of the variables have higher p values, you'll have to iterate it quite a many times. So this is something you have to look at. Now, so we have seen the probability value can be given by this NP. We can just write this equation and we'll get this. So this is one way of doing it. Another thing is we can simply use this predict function that will also give us. So what we'll do now is we'll understand one small concept called this quick board. Okay, so what we'll do now is just one more concept we learned, something called as confusion matrix. So what confusion matrix does is, it will kind of give you an understanding that, like, we know that okay, so let me put it something like this. So this is predicted, okay, 0, 1, and this is actual 0, 1. Okay, So what this matrix actually gives you is that how much accuracy have you achieved using the model, right? That you have calculated, you have made some prediction based on the p-values. So how many of it was actually zero and based on the predicted value. And again, remember, this predicted value will come from the probability threshold that you put. Like you can put it at 50% threshold, you can put that 60% threshold, like that. If you increase the probability values, accordingly, all these parameters will change. Like how many zeros were there when you have 60% probability and when you have 50% probability. So it will definitely change. So this number will kind of give you the accuracy. Like let's say that you have the actual value was 0 and you have predicted 0, right? And the actual value was 1 and you have predicted 1. So these are the accurate numbers that you are basically. So let's say that I'm just calling it A, B, C, and D. These 4 situations are there. So your accuracy will be defined as A plus B, which is the accurate number, divided by total, which is nothing but A plus B plus C plus D, right? You're getting my point? This is how accurate your prediction is coming out to. So this prediction will also change depending upon the probability threshold that you basically change. So if you change this probability, then this accuracy will also change. If you put the cutoff generally higher, 70%, 80%, then your accuracy will also increase. So this is how it will be usually. Am I clear? This is how the accuracy is defined. Very simple, right? That whatever accurate predictions we are making, the actual 0 is predicted as the is predicted as 0 and actual n is predicted as a 1, which I am just calling as A and B. So A plus B divided by A plus B plus C plus D. So if you put this number together, then you'll get some accuracy to the model. Am I clear? What is the accuracy of the model that we are getting? Am I clear? Hello?
Yeah, accuracy of the this logistic model, or
Yeah, accuracy of logistic model. See, what we are trying to do is we are trying to predict 0 and 1s, right?
okay.
So
When
whatever.
what is the prediction of value is yes, so we have to be not this one and
No,
one.
see, like this case, we have 168 data points, right? In this case.
Yeah.
Okay. So let's say that whatever number is, we'll see how many are actually 0 and how many are 1s. So let's say that there are actually, for the sake of this, there are 100 zeros and 68 ones. Okay, these are zeros and this is 1. Okay. So, or let me make it a little more easier. So what I'm saying is, this is actual and this is, and let's say that I have 1000 records, right? Okay, we'll keep 1000. Okay. That I have 1000 numbers. In 1000 numbers, the actual is coming out to be, 200 is 1 and 800 is 0. Okay, this is actual. And what we have predicted is 160 as 1 and the rest as 0. 840 as 0. Okay, this is what we have predicted. Am I clear? Hello?
You mean 200 means value?
No. See, I
I
am saying.
understand.
Okay, so I am saying that let's say that we had a situation wherein we had a record of 1000 students.
Yeah, okay.
Okay, 1000 students SAT score is there with us. Okay, for 1000 students.
Okay.
Now, in that, out of those 1000 students, 200 got the admission. Okay, and 800 did not get the admission. Am I clear? This is the actual situation that we have seen.
Okay.
Okay, but then when we have done the prediction, what we have found is that based on the cutoff that we have put, 160 people have been marked as 1 and 840 people have not been marked as 0. Okay, based on the prediction, because the prediction will be sometimes wrong also, right? That will happen.
Okay.
You're getting my point, because we cannot make 100% accurate predictions, right?
Okay.
So now in that,
Yeah.
out of this, let's say that what we are saying is that actual, so this is my actual and this is my predicted, and we are saying that actual is 200, right? So 200, so out of this 200, let's say that 140 is coming here and 60 is coming here. This means, and out of this, so basically this is 200 actual, and then 800 this. So out of 800, you have, let's say, got 700 and 100. Okay. So this is how, let's say that this is how our matrix is. The prediction that we are making is something like this, and the actual number. So basically, if you see this 200 is the actual number, right? That 200 actually people got selected. And how many we are actually predicting to be selected? 140, right? So for 60, we are missing out. Similarly, 800 people were there who were not selected. But so out of the 700, we have marked correctly. So this is correct prediction. This is also correct prediction. Okay. But then this is wrong prediction, right? These two are wrong predictions. You're getting my point?
Yeah.
Because they were actually the people who had been selected, but our model is saying that they have not been selected. So this is wrong prediction, and this is also wrong prediction. Okay, and these two are right predictions. So what is the accuracy in this case? Accuracy will be 700 plus 1 or 140, right? This is predicted. These two are predicted correctly, right? This was actually 0, and we have predicted it to be 0, and this is actually 1, and we have predicted it to be 1, right? Here you see. Am I clear?
Yeah.
See, when do you see it is right? When yes is a yes and no is a no. So in this case, no and no are predicted to be right. So 700 were actually not admitted, and we are saying 700 have not been predicted. So this is correct. Similarly, 140 is correct, and then we'll divide by 1000. So basically, 84% accuracy is what we'll get if this is a situation. Am I clear now?
Yeah.
Okay,
It's accuracy of the model.
Yeah, we'll see with the example also. The same thing what we have done for it. So what we'll do is, let's say, so for this data only, we'll use this method, and we'll see that how many actually rightly predicted and what is the accuracy that we'll get. So see, the same metrics that we're trying to just look at it, we can see it like this. So there is a function called prediction table. Okay, so results in the same logistic regression model, results log dot pred table. So see, this is how it is coming out of it. What this basically tells you, the same confusion metric that we have seen. So what actually tells you that when 67 people were actually admitted, and prediction also is the same. I mean, like 67 people were not admitted, and the model also predicted that they were not admitted. 87 people who were admitted, the model also predicted that they were admitted. 7 people were such who were not admitted, who were admitted, but model predicted that they were not admitted. So if you look at it, it's very, what will be the accuracy in this case? Accuracy is nothing but 87 plus 67 divided by these all numbers, which will add up to be basically 168, because we have 168 equals 67 plus 7 plus 7 plus 87. Right? Now is it clear to you that these two are accurate predictions, 67 and 87, and these two are wrong predictions? So if we just get this number, so what we are saying is this number is 91%, right? 91.6%. So we have made 91% correct predictions. Okay. We can actually make it more better. But then do you understand the concept of accuracy now? Hello?
Yeah, all fine. Thank you.
Okay. So if we can simply put it in like, we can just format it. Right now it is in an array form. So if you want to put it in data form frame, then it will look more kind of. So let's say I'm just saying confusion matrix. I just for a little more clarity. Okay, so this 0 and 101, you can just rename it. So column name you can put as cm dot columns. So this, the top thing is like prediction. So we can simply say it as pred 0. And this other thing is pred 1. Okay, and this is actual 0. So we can rename this also if you want. So 0 you can say also. Sorry. Okay, so this is how we actually look at it. That whatever was actual 0, we predicted to be 67, and out of them 0 were predicted to be. And this is again based on the 50% predicate off level. If you want to make it more, then you'll have to make certain changes, and accordingly you'll basically be able to reach it. So you can make one more column, and you'll decide at what cutoff level, if probability is greater than some number, you'll basically decide. Right now, this is based on the 50% mark. And why we are coming to the 50% mark is basically, comes from the fundamental that that how much lift we'll get. That if the model that we are choosing is coming out from the random situation, how much lift we'll get by adding the model. So this is also, it will kind of indicate that. So this will be part of it. So on the very generic level, we have just covered this part, logistic regression. That with very simplistic code, simple lines, very simple like theory and this part of it. What we'll do next is we'll cover it with a little larger data set in which we'll understand few more concepts, which I just start touching upon, that what is left, what is specificity, what is sensitivity. So there are few more concepts which will make this what is. So basically we have so right now we have just seen it from the accuracy. So there is one paradox here, right? So if you look at it, right now the data is not such. Otherwise, the paradox here is like, let's say that if in a data set, 90%, I'll just give you one understanding of how this will work. Okay, so let's say that there is an email campaign in which there's a company which is basically targeting 1,000 people with an email campaign to make some purchases. Okay, make purchases of a particular item. Now, out of this, usually the email, for the email campaigns, the success rates are very less. Like it's something around 1% or 2% or even less than that. So let's say that out of this 1,000 people, 10 people have responded positively, means they have bought the product using that link, and 990 people have not responded, right? This is the actual situation. So if this is actual, means this is 1 and this is 0, right? So this is my actual situation. Now, in this case, so basically, only 1% response rate is there. This is what it means. Now we have built a probability model, or this logistic model, okay? And from there, what we are seeing is that we have also, said something like this, that 98%, or let's say 99, for 991 people, we have said that, okay, they will not respond, and non-response. And maybe for 9 people, we have said that it's a response. It's still okay, and we can check, again, we can check that out of this 9, maybe 8 is coming from the same 10, and 1 is coming from some other population. So like this, it's coming. But let's assume, then you can still make some, figure out that how much accuracy you are basically achieving. Now let's imagine a situation that rather than saying this, if the model says that, okay, 100% of the people are not responding. Okay, this is what the model is saying, that everything is predicted out to be 0. If everything is predicted out to be 0, still what it means is that if everything is predicted out to be 0, then based on our confusion matrix, what it means is, this was for prediction, wherein this is 0 and this is 1. And over here you have actual 0 and 1. So what happens is, the prediction, all of the prediction is coming out to be, so all 1,000 is coming out to be 0. This means that nothing is here, so it's fine in the prediction range. But in actual situation, we know that there are 990 respondents, which is 0, and this is 10. Okay, but still based on the accuracy definition that we have created, what it will mean is that my model still is 99% correct, right? That we are saying that 99, because 990 are anyway, this 990 is anyway 0. So out of, if we are saying that all 1,000 is 0, if my model is saying that all 1,000 is 0, and actually the 99 is 0, right? then also this 99%, we'll get this 99% accuracy based on the confusion matrix. Am I clear, Dinesh? Shishir? Hello?
Yeah, I'm getting the point.
So basically it's kind of a paradox that this accuracy is not always the right accuracy, because we can say that, okay, my model is 99% correct, but what you have done is you have said that, okay, all 1000 is zero. So this in a way is not a correct model, right? There's a problem with this model. So there is a paradox involved here. But right now the data we have is kind of 67, 87. So this kind of problem will not occur. But over here in this kind of situation, so this is a kind of a paradox. What we'll see is we'll try to define few more, based on this understanding, we'll try to define few more things like specificity, sensitivity, and few other parameters like lift, AUC curve, which is area under the curve, which will give us more better predictive power. And this we'll do with little larger data set, with at least few more variables. So then that will make more of a sense. So this we'll do in the next section. So this essentially covers logistic regression, like at least in the very, very basic minimal form, this is what logistic regression is. But we'll kind of refine this process even more so that we'll be able to define this accuracy, like these kind of paradoxical situations that, it's not kind of twisted in one way. Like if a lot of it is negative or positive and model is saying all of it is in the same direction, then it will not make a lot of sense. So these kind of problems will be eliminated if we define and refine a few more parameters of accuracy and precision. So this we'll do with a little larger data set, which we'll do in the next section. Okay. Any questions you have?
No questions. So are we concluding the session today?
Yeah, we'll conclude the session. In the next in the next class, we'll take these things forward with little larger data set.
Okay, perfect. Thank you. Take care.
Okay. Any other questions, Santa?
No. Thank you. Have you uploaded the code?
I'll upload it. I'll upload it either now or maybe tomorrow. I'll upload it because it's not. Okay.
Okay.
Thank you.
So gpadmission.csv, where will this get? Have you?
Okay. Either today or tomorrow.
Okay. Thank you. Okay.
Okay. Thank you.
Thank you.
Thank you for attending the session. I hope you all enjoyed it. Don't forget to visit our Vimeo page and follow for more upcoming videos.